This is example number 4, and before we do it, we're going to talk a little bit about how we determine what the acceleration due to gravity is for any particular planet. We know that if you're right here, your force that you feel due to gravity is m times g. And we just learned that if you have a really massive planet, that the force due to and its gravity is essentially your mass times the mass of the Earth, all divided by the distance between you and the Earth, or the center of the Earth, squared. We can also plug in, if you remember, that universal gravitational constant, which is 6.67 times 10 to the negative 11th. If we set the two equations equal to each other, so we're just going to take the mg here and we're going to move it. Here we go. So let's move it over here. We'll notice that if I take you and make you the appropriate size in order to put you on the Earth, so there you go, you're almost the appropriate size, you're close enough, I guess, and I move you and put you on the Earth, and we'll put you somewhere there in Indiana, you really don't matter. You're just way too small. So what we can do is we can go ahead and let's cross off your mass and get rid of it. And now we notice that if we want the gravity for any particular planet, we can say that that gravity, or acceleration due to gravity, is equal to big G times the mass of that planet divided by the distance between you and the center of the planet squared. So the further away you get from a planet, the less the effect of gravity that you feel. The smaller the planet, the less the gravity that you feel. And so those are some relationships that we need for the problem that we're about to do. Timba is standing in the lunch line, and Timba is 6.38 times 10 to the 6 meters from the center of the Earth. They know the Earth's mass is about 5.98 times 10 to the 24th kilograms. Let's go ahead and write some of these distances and masses down. So we know the distance from Timba, so here's Timba, to the very center of the Earth. So let's go ahead and move the person somewhere on the, right on the surface of the planet. They're in a boat, I guess. And we know that the distance from here to the very center of the Earth, so it would not be to Central America here. It actually is the very center of the Earth, where it would be hot and it would not be very pleasant to be. That distance is 6.38 times 10 to the 6 meters. 6.38 times 10 to the 6 meters. We also know that the mass of the Earth is 5.98, so 5.98 times 10 to the 24th kilograms, and so that would be the mass of the Earth. They want to know what is the acceleration due to gravity on Earth. So let's use our equation. G is equal to big G times the mass of the planet, or the mass of Earth, all divided by the distance between you and the center of that planet. This is equal to 6.67 times 10 to the negative 11th. And we will multiply that times the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, and we'll divide it between you and the center of the Earth, which is about 6.38 times 10 to the 6th meters. Make sure that you square this. This is where most people make a mistake. If you go through and do your math, you'll notice that the gravitational acceleration between you and the Earth is 9.80 meters per second squared. And remember, we've been using 10 just because it's easier to multiply and divide. But for this problem, we're going to go ahead and use 9.8 because that's exactly what the gravity, or the gravitational acceleration between you and the Earth, would be. For part B, it says, when Timba eats his lunch and his mass increases, does this change the acceleration due to gravity? No. If you remember, your mass does not matter. What matters is the mass of the planet, or of the larger object of the two. And that's the end of this example.